Welcome to Chapter 5. We're finally getting into the trig part of this course that's called Precalculus and Trigonometry. So, in trigonometry, which I think I'll just abbreviate trig, okay, positive angles are measured counterclockwise from the x-axis, or from the positive x-axis. Okay, so obviously we need the x-axis, okay, the positive one is the one on the right here, and if I'm measuring a positive angle, I need to move here and go in the counterclockwise direction, okay. So this angle that's formed from the x-axis all the way to this stopping point. The stopping point is called the terminal side. And the x-axis is really called the initial side. So where it initiates, where it terminates. And we will most often call an angle referenced by a Greek letter. So this is Greek letter theta, okay? So there's a positive angle theta. If we wanted to measure a negative angle, okay, then we would go clockwise. So negative angles are measured clockwise, still from the x-axis. That just gives us a common orientation for what we're going to be talking about, okay. As a definition that will be important, angles are coterminal. Alright, so that's what we're defining. What does it mean to be coterminal? If they have the same initial and terminal sides. And we'll have a visual and an example to go along with this, okay? So as an example, suppose we want to find two positive and two negative coterminal angles for theta equals 60 degrees. Okay. Now this is trigonometry, it's not geometry, okay? So we don't need to go through all the differences, but basically you're not going to need a compass, you're not going to need a protractor, but you do need to have some sort of an idea about where 60 degrees might lie, okay? So I'm not saying you have to measure it perfectly, it's more of a sketch. Where is it, okay? So where do we start? We start at the x-axis, so that's 0 degrees. If I kept going until I was perpendicular, that would be 90 degrees. Halfway between would be 45. So 60 degrees is actually halfway between 45 and 90. So I'm just going to kind of estimate that and call it theta. Okay, so this is our 60 degree angle. And now I've got to go about finding coterminal angles. Okay, so if I want to find some positive angles, let's start there. Two positive coterminal angles. I still have to have the same initial side. So I still need to start at the x-axis and the same terminal side. But how I get there is just, I need to go counterclockwise. So here's one way in which I can do that. I could start at the x-axis, pass the angle, wrap all the way around, and then stop at the angle after, or stop at that terminal side after I go all the way around once, okay? So what is the measurement of that angle? Okay, so one of the positive angles, the one we're calculating right now, was I went once all the way around the circle. That's 360. And then I went an additional 60 so I could end at the right terminal side. So 360 plus 60, maybe I'll put this as scrap work, is 420. So I've got a 420 degree angle that is coterminal to the 60. And I can do this same idea, okay? So if I maybe bypass that angle again, wrap all the way around, and then stop at that terminal side. So now I've gone around twice. Once around the circle 360. A second time is another 360. And then 60 degrees to end at the terminal side. So I have another 360 that I built in. So I've got a 360 plus a 60 plus another 360. So 780 degrees is another coterminal angle. Okay, so maybe we can start to notice a pattern here. How did we get from the 60 degree to 420? How did we get from the 420 to 780? Okay, oh, we're always adding this 360 degree angle, okay, to get to another one. So for negatives, well, maybe you already have a hypothesis. If not, take a pause. What do you think you're going to do for a negative angle? Okay, the positives are going to add 360, and the negatives I have to move in the other direction. You know, is there an idea that might work here? Okay, so I'm going to try to erase some of these extra lines, all right, and then we can talk about, well, what's going on the negative side. So let me put the axis back in. Okay, still has to start out on the x-axis, but I need to travel negative, so I gotta go clockwise. Still need to stop at the terminal side. Okay, so this angle is coterminal to 60 degrees, but because I went clockwise, it's definitely going to be negative. Okay, negative what though? Okay, so if I had gone all the way around the circle, that would be 360. I didn't go all the way around. I fell short of going all the way around. So how short was I? 60 degrees short. So from that 60 degree angle, I went negative all the way around. So that's going to give me an angle of negative 300 degrees, okay? Maybe this subtraction isn't the best way to explain it. I actually like how I was thinking about it at first. 360 is all the way around. I'm 60 degrees short of that. So I've gone 300 degrees, but I've done that 300 degrees in the negative direction, okay? Now I need another one. I have two negative. So let's say I don't stop there the first time, come all the way around, and then I stop after traversing the whole circle once, okay? So I go all the way around, that's negative 360, and then I do the same thing I just did, which is the negative 300. So negative 300, negative 360 is negative 660. Okay, so think about it again. What's the pattern? What happened here? From 60, subtract 360. Okay, that's how we got negative 300. To get from negative 300 to negative 660, that's another subtraction of 360 degrees. So I can always find these coterminal angles by either adding 360 or subtracting 360 continuously. So actually there's infinitely many ways to do that, okay? All right, speaking of this 360 idea, okay, the idea of 360 degrees, have you ever considered why? Why do we say a circle has 360 degrees? You know, where does that come from? I mean, we could measure it a different way perhaps, and we will in a moment, but why 360? Is 360 a significant number? Okay, obviously we know that's how many degrees in a circle, but why does it have to be that way? Okay, well, historically, right, so if we go at ancient times, civilizations couldn't really calculate exactly the number of days in a year, but they would roughly estimate the number of days in a year to be about 360, right? We know it's 365 and a quarter, that's why we have that leap day. But if you're an ancient civilization, 360 seems fairly reasonable. So 360 became a very important number to cultures like the Babylonians, and that's why we still use 360 degrees in a circle. But this choice is quite arbitrary, actually, and we don't have to always use this 360, right? Think about if you're measuring your height. You could measure it in feet and inches, or you can go over to the metric system and measure it in meters and millimeters, okay? So there's different ways that we can measure the same object here, okay? So degrees is one way which you can measure an angle. We're going to talk about an alternative measure of an angle that is going to be far more important than degrees. That's another reason why we're not really getting into protractor stuff. Most protractors are built in degrees, okay? So this way of measuring an angle might not be as familiar, but this is something we're going to continue to develop. So a radian is an angle, or let me say not a, let's say 1 radian. all right? So it is a way to measure something, like saying 1 meter or a yard or a foot. 1 radian is the measure of an angle formed when arc length equals radius. Okay, so we're going to need to visualize this. We know what a radius of a circle is. Arc length, maybe you remember, maybe not, that's okay, but we start with a circle. All right, we've got our radius. Let's call that R, okay? I want to measure an angle now in such a way that this arc length is the same as the radius. So I don't really have a piece of string, but somehow I want to measure a curvy distance here, okay? So if I had a piece of string, I would lay it real tight on this R, and then I would come over here and transfer it to the outer circumference of the circle. And I would try to measure it so it's the same. So I need strings that need to be flexible so I can measure a curved distance. But I'm looking for this R to be the same as part of this curve. So if you can kind of imagine, I'm estimating here that this R is the same as this curvy distance. They have the same length. And of course, this extra side that I just drew that forms the whole angle here, that's another radius. Starts at the center, goes to the other side. So look at this nice symmetry here. Radius, radius, radius. They all have the same distance. That angle in here is 1 radian. And that will be true for any circle, no matter how big or how small I drew that circle, as long as the radius here is the same distance as the arc length there, then I'm going to get an angle that is 1 radian, okay? So radians have this nice symmetry versus the 360 has this nice history, okay? Since circumference, all right, circumference is the distance all the way around the circle. Maybe you recall this formula from a geometry class. Okay, circumference, if I go all the way around the circle, that measurement is 2 pi r. So what that tells me is that 2 pi radians make up all the angles in the circle, right? If I go all the way around, I have all the angles, 2 pi, okay? So 2 pi radians is all the way around. Well, 2 pi radians is 360 degrees, okay? So what I'm trying to do here is get an equivalence, right? Like 3 feet is a yard, 12 inches is a foot, okay? Here's our equivalence between these two measurements. 2 pi radians is 360 degrees, or this simplifies, they're both having a factor of 2. I can say pi radians is 180 degrees. Let me build onto this original visual to see where maybe this pi idea comes from. This angle in here, so if I do another one of these, maybe I call that one another radian, right? Trying to get all these radii the same. And maybe I call this one another, okay? And then I've got another radian, and then I've got another radian, and then I've got another radian. Okay, I can get about 6 radians in here. 1, 2, 3, 4, 5, 6. And then I have this extra sliver left over. That extra sliver right over is not a full one, okay? So 2 pi is like 6.28, okay? So I got 6, and then this extra sliver is like the 0.28 that gets me to pi radians, okay? Same thing here. When I did 3 radians, 1, 2, 3, I don't quite get to 180 degrees. I'm a little bit short. That's why I need 3.14, okay? Dot, dot, dot. So pi radians is 180 degrees. It's a little bit more than 3 to get to halfway around the circle. Okay. So we need to be able to comfortably convert between these two, because you're probably more comfortable right now in the degrees, but we need to transfer that comfort over to radians, because that's what a lot of our computations are going to continue to be in. So let's convert a 60-degree angle to radians. Okay, if you have this memorized, maybe from a previous trig class, make sure you still understand how to do this conversion in case the one on the test is not one you have memorized. And make sure you can go the reverse direction. Convert 5 pi over 6 radians to degrees. So 2 problems in one here. All right, 60 degrees. What I'm going to cleverly do, right, mathematics can often be very clever, is I'm going to multiply by 1. So if I multiply by 1, I'll still have the same angle, and I can still say we're equal, okay? But I'm going to multiply by a very clever version of 1. If these are the same thing, pi is 180 degrees, or pi radians is 180 degrees, multiplying by pi, dividing by 180, that's just multiplying by 1, right? That's like saying, oh, 3 over 3 is 1, right? Because 3 is himself. But if these are equal, pi radians over 180 degrees is also 1. So here's our clever multiplication. Multiply by pi radians, I'm going to abbreviate radians just to rads, and simultaneously divide by 180 degrees. These are the same thing. They're the same angle. I'm multiplying by 1, so I still have equality. The reason why I want degrees in the denominator is, well, degrees are in the top here, they're in the bottom here. I just canceled those units, and I'm left with the result. If you need help multiplying these fractions, pretend that's over 1. I have 60 pi over 180 radians. Let me simplify this further. 60 goes into 183 times. Pi stays pi. So I have pi over 3 radians. Okay, I'm going to do something similar here. Maybe progress a little bit quicker. If you want to pause the video at this point, do so. See if you can do this one on your own, and then just check in. I want radians to cancel. So I'm going to this time divide by the pi radians, but multiply by the 180 degrees. In this way, the radians cancels. The pi also cancels. And let me do a little bit more simplification. 6 goes into 180 30 times. So I've got 5 times 30 left over. Denominators are both 1. And I have 150 degrees. Okay. So notice I'm either multiplying by pi over 180, so the degrees cancel, or multiplying by 180 over pi, so the pi's cancel. Those are the only 2 things I'm going to do. Okay. We need another formula here for something that may be coming up, and that we've already mentioned, arc length. We talked about arc length and we defined a radian. That was the little piece on the circumference of the circle. So arc length on a circle, or let's say arc length S on a circle of radius R, is calculated by S equals R theta. Okay, I make my S's script so they don't start to look like 5s. Okay, I really just want that to be an S, not accidentally misconstrued to be a 5. When, and only when, theta is in radians. Okay, so here's another important point. Why aren't we using degrees all the time? This formula doesn't hold for degrees. It holds for radians only, okay? So let's visualize what's going on there. Here's our circle. Its radius is R. We do some sort of a theta. And then arc length. Maybe I'll change colors. Hopefully that shows up okay on the video. Maybe with a slightly better marker it will. That black distance, that's your arc length. That's your S. So this formula gives us a way to measure curves of a circle. That's great because I don't have a device, like a ruler isn't really going to help me measure a curve that well. But this formula allows me to do that, okay? So that's fairly handy. If theta is all the way around the circle, 2 pi radians, then the arc length is R times 2 pi. I'm going to write that as 2 pi R, which we've already seen in this video, which might have already been familiar to you. This is circumference formula. What this is saying, let me modify the picture, is if I had traveled all the way around the circle, then the arc length I'm calculating is all the way around here. And thus we get circumference formula. So the point of this is saying, okay, instead of memorizing some brand new formula, if you already were familiar with this one, this formula is now all you need. I don't need both of these formulas. I really only need this one right here. And if I use theta is all the way around the circle, I know I'm talking about circumference. So trying to make connections or building on existing knowledge rather than memorizing all these separate things out there, okay? Lastly, I want to talk about a type of speed that we can measure on a circle, okay? Because, you know, if we think about traveling, okay, bicycle, car, a lot of objects have wheels. So we might want to be measuring speed of some sort of a wheel, okay? So recall that speed can be defined as, it's a rate, right? Think miles per hour. Miles are a distance, per hour is a time. So speed is just distance per time, okay? Just like a slope, right? It's a rate of change. So there are two ways to measure distance on a circle or a wheel. Distance can be measured by how far a point on the circumference travels. And we call that linear speed. That's probably your more familiar miles per hour or feet per second type speed, okay? Or by, so here's an alternative, can be measured by either how far a point travels, or alternatively by the angle formed by the wheel or by the circle as it rotates. That one maybe is a little less familiar, but we'll go through an example about how these might compare. So suppose you have a wheel with a 24-inch diameter. Diameter is just all the way across the circle. That means you have a 12-inch radius. Okay, keep that in mind. And it rotates at a rate of 800 revolutions in 1 minute. You might see that as RPMs. Okay, so that means like this is rotating, goes around 800 times in 1 minute. Okay, so it's moving pretty fast, but I want to know how fast. Like what is that in terms of speed, okay? I did forget to define this one. The angle formed by the circle is called angular speed. And for this particular wheel, we're going to find both the linear and the angular speed, okay? So for linear speed, if I want to get a good sense for what's going on here, I'm actually going to figure out the linear speed with the units miles per hour. Okay, so where are we going to start? We start at the rate that's given. I'm given 800 revolutions occurring every 1 minute. I'm writing that in a fraction notation so I can start canceling things the same way we did unit conversion. All right, I need revolutions not to be here. I want miles and I want hours, okay? Let me actually attack the minute part first. I think that's slightly easier to understand. I don't want to be in minutes, I want to be in hours. So I need to say, okay, well, how many minutes are equivalent to an hour? 60 minutes are equivalent to 1 hour. And by putting minutes in the top, I can cancel those units, and now I've converted myself to hours, okay? I'm going to do the same thing. I need to convert revolutions somehow to miles. It's going to take a few steps. I need revolutions to cancel. So that's where I start. I put it in the denominator so they'll cancel. But 1 revolution is how much around the circle? That's the topic we were just talking about. If I go once around the circle, 1 revolution is the circumference. That's 2 pi r. And in this problem, r is 12. So I'll have 2 pi times 12. And the units are inches for that. Inches. So I'm in, what units are left? Inches per hour. I want miles, okay? But this is familiar, right? I'm not going to jump straight into miles, but I know how many inches are in a foot. 12. Put inches in the denominator, so they cancel. And I know how many feet are in a mile, or I should, 5,280 feet. If I didn't know that, I could look it up. Are in 1 mile, so feet cancel, okay? So at the end, I just have a huge fraction that I have to multiply. Everything in the top gets multiplied. 800 times 60 times 2 pi times 12. Then divided by everything in the denominator. So dividing by 12, divided by 5,280. Let me write down the work so we know we're grouping things properly. 800 times 60 times 2 pi times 12. All divided by, open up those parentheses, 12 times 5,280. So when you're typing this in the calculator, both of these quantities have to appear in the denominator. Those parentheses as written will do that for you. This is approximately 57.12 miles per hour. Okay, so you know we're going at like maybe not quite highway speeds, but faster than what we should be going down Old Shell Road or something like that. Okay, so angular speed will be measured in radians per minute. These will be given in a set of directions. What kind of units do you want? I'm going to start in the same place, 800. 800 revolutions occur every 1 minute. Okay, so I don't need to change myself to minutes to hours. I've got that already, but I do need to change from revolutions to radians. So I need to cancel a revolution and figure out how many radians are in 1 revolution. Don't memorize. Think about what this is saying. Once around the circle. How many radians is that? If you're not sure, think, how many degrees is once around? 360. Okay, rephrase. Now, how many radians were 360 degrees? Once around the circle was the definition of 2 pi radians. So this, I have 800 times 2 pi. The revolutions have canceled, and I get 1,600 pi radians per minute. So that's how many angles, right, are kind of being formed as this guy rotates or revolves around. He's forming 1,600 pi radians every minute. Still a speed, just not a speed that maybe you've seen frequently, okay? Make sure you kind of understood how to do these unit conversions. These are big in chemistry, and they're also going to be big in this section right here.